Hi everyone, welcome to Mathemly. Hi everyone, and welcome to our series on neural networks. In this first video, we are going to explore why these powerful systems were created in the first place. We will start with some simpler models and see where they fall short, leading us to the need for a more advanced solution. Let's dive in. Let's begin with a basic model for classification, like logistic regression or a simple perceptron. The goal is to separate data into categories. For example, predicting whether a person has a high or low risk of diabetes based on features like height and weight. These models try to solve the problem by drawing a straight line called a decision boundary that separates the two groups of data points. If the data is simple and linearly separable, meaning one straight line can clearly separate the categories, this works really well. For instance, imagine plotting a group of patients on a graph with weight on the x-axis and height on the y-axis. If all the high-risk patients are mostly heavier and taller, and low-risk patients are mostly lighter and shorter, a single straight line can divide them effectively. The model learns the best position and slope of this line to classify new patients correctly. This approach is intuitive and easy to visualize, which is why these simple models are often the first step when exploring classification problems. They help us understand how features relate to outcomes before moving on to more complex methods. But real-world data is rarely that simple. Often, the outcome depends on a combination of multiple factors, not just one or two features. For example, a person's risk of diabetes may depend on a mix of height, weight, age, diet, and exercise habits. The relationship between these variables and risk is usually non-linear, meaning it curves or twists rather than forming a straight line. Imagine plotting data points that form a circular pattern. One group in the center, another surrounding it. No matter how you draw a straight line, some points from each group will always be on the wrong side. Linear models like logistic regression or a single layer perceptron simply cannot capture these patterns. Even if we add more features, linear models are still limited because they combine features in a linear way. They cannot bend or curve the decision boundary to fix complex structures in the data. As a result, predictions become inaccurate whenever the relationships are nonlinear. This limitation is one of the main reasons why more flexible models capable of learning nonlinear patterns are needed. Now that we have seen how linear models fall short, the natural question is, how do we go beyond straight lines? This is where neural networks come in. Instead of being restricted to just a single weighted sum of inputs, they introduce nonlinearity through layers of transformations. Let's break this down. Think of each neuron in a neural network as a tiny decision maker. It takes in information, applies a weight, adds a bias, and then, most importantly, runs the result through something called an activation function. This function is what bends the straight line into curves, corners, and flexible shapes. We will discuss this section in depth in the upcoming videos. When you stack many of these neurons together across layers, the network gains the ability to model very complex patterns. It's like combining multiple pieces of curved glass. One layer bends the data slightly, the next layer bends it more, and after a few layers, the network can wrap itself around even the most complicated data structures. So, going back to our circular example, while a linear model is stuck drawing only straight lines, a neural network can gradually build a decision boundary that curves around the inner circle perfectly, separating the two groups. This idea of stacking layers and introducing nonlinear activations is the key that allows neural networks to go far beyond the limits of linear models. It is what makes them so powerful for problems in vision, language, medicine, and just about every modern AI application you have heard of. Now, let's make this more concrete with real-world examples. Neural networks are not just abstract math, they are behind many of the technologies we use every day. Take voice assistants like Siri or Google Assistant. They rely on neural networks to understand spoken language, recognize accents, and even pick up context from conversations. Or think about image recognition. whether it's unlocking your phone with facial recognition, detecting tumors in medical scans, or helping self-driving cars identify road signs and pedestrians. Linear models would completely fail here because the patterns in images are highly nonlinear and complex. Another example is recommendation systems like Netflix suggesting what you might want to watch or Amazon predicting your next purchase. Neural networks analyze millions of data points, spotting subtle patterns in your behavior. These real-life cases show why neural networks aren't just better models. They are often the only models capable of handling the complexity of real-world data and delivering accurate and meaningful predictions. In this video, we explored the journey from simple linear models to the need for neural networks. We saw why linear models struggle with complex data and how neural networks provide a flexible and powerful solution. In the next upcoming videos, we will dive deeper into the core structure of neural networks, exploring hidden layers, neurons, and activation functions to see exactly how these systems learn. If you found this video helpful, don't forget to like, share, and subscribe to Mathemly for more data science tutorials. Comment below with what you would like to learn next. Thank you for watching and see you next time.